Let's talk about physics, 1136, and this is some problems from page F. And in reading over this section, I don't know about you, but that term elastic to me has a different meaning than the way it's used in physics. So for instance, go back and look in your PACE at page 10. And if you were to look at these things on this chart, coefficients of collision, and you see lead, copper, brass, elm, cork, rubber, and glass and steel, and you're saying, I wonder which one of those is the most elastic. You might think, I know what it is. It's rubber. You know, like elastic rubber bands. That would be the most elastic. Or maybe it's cork, you know. Push on it and then it kind of rebounds and takes its shape again. You think, I bet it's cork. You know, cork and rubber would be the highest. And yet they're saying that the most elastic material on this chart is glass. Yeah. So in physics, sometimes words have a different meaning than our normal experience. We think of elastic as meaning you can stretch it. And you think, well, glass, you can't stretch glass, so it's not elastic. But in physics, what elastic means is that after a collision, it retains or bounces right back to the shape that it had before. So if you think of two marbles and you roll the marbles towards each other, they're going to bounce off each other practically perfectly. They're going to have exactly the same shape, even if you hit them hard, okay? Whereas it sounds like if you take lead, in fact this is true, a lead bullet, when it is shot at something, it doesn't bounce off, okay? Like a steel ball might. When it hits something hard, it actually changes shape and becomes a new form and just kind of melds into whatever it hits. And copper and brass also. If you hit it really hard with a hammer, it doesn't just bounce back. Steel will bounce back. But copper and brass can be hammered, okay? So they actually, again, I want to say they're more elastic. It's not what they are, okay? Elastic means it retains its shape, and inelastic means that it changes shape. Isn't that weird? So elastic doesn't change shape. So yeah, it's kind of a mind bender. Sorry about that. All right, let's talk about the math here on page F. We have two formulas that we're going to use. One is the coefficient of collision. And the formula is we take the velocity that something separates after the collision and divide by the velocity at which it is approaching or hitting something. So problem number 90 is talking about a ball, and it hits a surface, and as it's approaching, it hits with 50 centimeters per second, but then it rebounds only at 30, okay? So it's not perfectly rebounding. At the same speed, it's a little bit different. So we take the speed that it is separating, which would be the departure here, divided by the speed that it's approaching. When you divide those two, you get a decimal number, and that's what you would expect the answer to be, okay? And number 91, by definition of being perfectly elastic, that means this coefficient has to be 1. So the exact speed that it approaches, it's going to rebound at exactly the same speed, okay? So I'm going to let you figure out that one. Let's look at number 94. 93 is an application of this as well, but that one's pretty easy. 94 says the formula for strain is the change in length divided by the original length. So let's say we have a piece of elastic band, okay? And you stretch it to just its normal length, measure that, and then if you stretch it some more, you're not taking the whole thing divided by the original, you're taking just that difference, the change in length. So you take the longer length minus the original length, that's the change in length, and divide that by the original length. Okay, so looking at 94, it says, what is the strain on an elastic belt? 72 centimeters long, buckled around a person whose waist measures 80 centimeters. So the original length would be the 72, okay? But we're making it stretch out to 80. We don't put 80 up here. What's the difference between 80 and the original length of 72, okay? So I'll write it as a little math problem here, 80 minus 72. So you solve that first, find out what's the length that it changed, and divide that by the original length. That's how we do these strain problems, okay? Let's look at 95 over here. 95, we'll come back to some more strain problems for 96 and 97. 95 says a coiled spring, when it's stretched with a 1 Newton meter, 1 Newton object, weight mass, has it stretches 0.05 meters, okay? So the rule, Hooke's law, says that if you double the weight, okay, then that also will double the length. And so if we triple the length, going from 1 Newton to 3 newtons, that's times 3, 1 times 3, then we'll do the same thing with the length. So you'll take the length, double it if we were doing this one, triple it for this one. If it was 4 newtons, then it would be 4 times the length, okay? Let's come back over here now and look at number 96. A little different application of this same formula. 96 is a spring on a screen door experiences a strain of 0.5 when the screen door is opened. If the change in length is 20, what was the original length? Okay? Now if you remember how to do magic triangle problems, this is like in the top, and this over here is in the bottom, and we're solving for the length, so we can take the top, divide by the bottom, and you have this number. Okay, there's other ways of doing it. You could multiply both sides by L to cancel out, and then divide by the, take the 20 and divide by the 0.5. But anyways, that's how you're going to solve that. And that's what they're solving for, is what was the original length. Now this one, 97, is a little trickier, okay? Let's read it. It says, the elastic in a slingshot experiences a strain of 3.4. If the original length was 15, what is the length just before it's released? Okay? Now, we're going to solve for delta L, but that's not the answer. That's part of, we're getting closer to the answer. So the original length is 15. Then we're going to multiply that times 3.4, and that's how much it changes, okay, the change in length. But to get the total length, which is what it's asking for, what was the length of the slingshot before you let go, we have to take the change in length and add it to the original length, okay? So it's kind of tricky in the way they ask that, trying to make you think about that, which is why it is called a think problem, okay? But it's just another application of using this formula. Delta L, change in length, divided by the original length, is the strain. Okay, hopefully that will help you with those problems on page F. Make sure you score that. If some of that did not make sense, when you go to the score key, at the very back of the score key, as you know, is the solution manual, which shows all the steps for solving those problems. And that will hopefully help you. And then you're ready to do your checkout.